All right, so let's talk about some electron configurations of elements. You might have looked at these before in a previous chemistry course. And we did talk a little bit about listing the orbitals up to 6p at the end of the previous lecture. So what we're doing is listing the orbitals in order of increasing energy because that's the order they're going to fill up in. The electron coming in is going to take the orbital, the subshell that has the lowest energy. And then there is another rule, we'll show it in this second example, that when you do have many orbitals that are the same energy, you're going to put one electron in each of those orbitals first before you go back and double up. So we'll see that in this second example. First, let's go ahead and list the orbitals in order of increasing energy. We did that at the end of the last lecture. Let's take a look at your textbook actually. So the last lecture we looked at this rain on the roof method of looking at the order 1s, then 2s, then 2p, then 3s, then 3p, then 4s. There's another way to look at it. Some students prefer this rain on the roof method. Others prefer looking at the periodic table. So the shape of the periodic table has to do with these electron configurations. That's why it has this weird castle-like shape. We got a tower on the west side, a tower, like a thicker tower on the east side. Anyway, these two columns, this thinner tower has two columns, and that's because the s orbitals are filling up with 2 electrons. And once you've reached the second electron, that s orbital is full, you start doing a different type of orbital. This tower over here is much thicker. It's 6 columns because the p orbitals take 6 electrons before they're filled up. So the first electron to fill up, these little kind of turrets over here, are the 1s orbital. Only 2 electrons fit in there, one for hydrogen and one for helium. After you get to helium, you're done with the 1s. The next one to fill up is the 2s. So lithium and beryllium are filling the 2s. After 2s comes 2p. So that starts with boron and goes all the way to neon. Those 6 elements are filling up 2p because it can fit 6 electrons. Then comes 3s, and then comes 3p. Then comes 4s, and then this sunken area over here, this moat, I guess, of the castle, is the D area, but remember that the D is one level behind. So when you're on the 4th period filling up the 4s and the 4p, the D area is filling up the 3D, not the 4D. So it's one level behind. Then we go to 5s, and then 4D, and then 5p, and then 6s. After 6s, kind of hidden underneath lanthanum, is the lanthanides. That's where we're filling up the 4f. So that's kind of like the dungeon of the castle, and it's 14 columns because it takes 14 electrons to fill up the 4f, and it's 2 levels behind. So when you're filling up the 6s and the 6p in period 6 of the periodic table, that's when you're filling up the 4f, so it's 2 levels behind. Then the 5d, it's 1 level behind, and then the 6p. And so that's about as far as we're going to get here. Let's summarize that and put it in order. It is 1s, then 2s, then 2p, then 3s and 3p, then 4s, then 3d, then 4p, then 5s, then 4d, 5p, 6s, 4f, 5d, and 6p. So that is the orbitals in order of increasing energy. So you can remember that either with the rain on the roof, or by using the periodic table, or by just writing it on your note card. But remember that that's the order that they should go into. So the orbital diagram shows these orbitals as boxes. So we're going to do the element fluorine, which is element 9 on the periodic table. There are 9 electrons. And they are going to use this order and start filling up orbitals. And once we've reached 9 electrons, then we're done. So the first orbital is the 1s. We're going to represent that with one box. Then comes the 2s. Then comes the 2p. And that's all we're going to need actually. The first 2 electrons will go into the 1s orbital, but we still have 7 left. The next 2 will go into the 2s orbital. We still have 5 left. Then the 2p orbital, this is where that Hund's rule comes into play. There are 3 orbitals that are all the same energy. So we put 1, 2, 3 all spread out before we go back and double up. 4, 5. So 2, 4, 6, 8, 9. Those are the 9 electrons for fluorine. And this is the orbital diagram. The electron configuration just has the names of the orbitals, and then instead of drawing a box with arrows, you represent those electrons as a superscript. So this would be 1s2. There's 2 electrons in the 1s orbital. 2s2, 2 electrons in the 2s orbital. And 2p5, there's 5 electrons in the 2p orbital. So this is the electron configuration over here, and this is the orbital diagram over here. All right, we're going to start off drawing some electron configurations of noble gases, because these are the elements that have a complete shell. And all the other elements are trying to get those complete shells. So all the other elements are trying to copy these noble gases. They're trying to look like them. Kind of like these are celebrities and movie stars. Everybody wants to be cool like them. All the other elements want to try to get to be who these guys are, either by forming ions or by sharing electrons. So helium has 2 electrons, and both of those fit in the 1s orbital. Neon has 10 electrons. The first 2 fit into the 1s, the next 2 fit into the 2s, and the next 6 fit into the 2p. Argon has 18 electrons. I should put some charges on these electrons. So we have 1s2, 2s2, 2p6, 3s2, and 3p6. 2, 4, 10, 12, 18 electrons. Krypton has 36 electrons. After 3p6 comes the 4s, then the 3d, which can fit 10, and then the 4p, which can fit 6. Xenon has 54 electrons. Let's write a little smaller to fit all those. All right, xenon is found at the end of the 5th period, and so it has the level 5 shell being filled here. We have 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 54 electrons. Now we want to address this concept of valence electrons. These are the electrons in the outermost shell. And this is really important because when 2 atoms approach each other, what's on the outside is the electrons. The nucleus and the protons and neutrons are way inside. So the electrons are on the outside. That's what the other elements see when they come into contact with a certain element. And the outermost shell is the ones that they come into contact with first. So this determines a lot of the chemistry of the elements. And it's also why you see these electrons configurations following a pattern that mimics the periodic table, because that's what their chemical properties follow as well. So for the outermost shell of helium, that's pretty easy. It only has one level, level 1, and the number of electrons in level 1 is 2. For neon, the outermost shell is the level 2 shell, and there are a total of 8 electrons in that shell. For argon, the outermost shell is the 3rd one. There are 8 electrons in there. For krypton, the outermost shell is the 4th one. There are 8 electrons in there. And for xenon, the outermost shell is the 5th one, and there are 8 electrons in there. So this is where we get what's known as the octet rule, which is that all of the elements are trying to get to 8 electrons in their outermost shell. So they can be like the noble gases. There's a little bit of a variation on this rule in that hydrogen and helium can only fit 2 in their outermost shell. And so all the other elements are going for 8 electrons. Hydrogen and helium are too small to handle 8 electrons. They're going for 2. So let's draw a few more electron configurations that are not of the noble gases. Lithium has 3 electrons. The first 2 are in the 1s orbital, and the next one is in the 2s orbital. So the 2s orbital is not full, but that's where that last electron can fit. And so the outermost level for lithium is level 2. If we want to keep track of the valence electrons, altogether there's 1 valence electron for lithium. Sodium has 11 electrons altogether. The first 2 are in the 1s, the next 2 are in the 2s, the next 6 are in the 2p, and the next one is in the 3s. So its outermost level is level 3, and there's 1 valence electron there. And lithium and sodium are in the same family, so it's not surprising that they have the same outermost shell, the same kind of chemical properties there. All right, so what do we mean by an abbreviated electron configuration? So the abbreviation for an element's electron configuration uses the noble gas that's 1 level up. If you look on the periodic table, lithium is in period 2. You go 1 level up to period 1 and you see that helium has this electron configuration. So this is the same as helium. We could represent that as helium's electron configuration. So lithium has helium's electron configuration, and then in addition it has 1 more electron in the 2s orbital. For sodium, if you go 1 level up, that noble gas in the 2nd period is neon. Sodium's the first element in the 3rd period. So you go up to the 2nd period and then you find neon all the way to the right. So this is the electron configuration of neon. If you look at the previous table we did, 6.4.3, find the electron configuration of neon, this is exactly it. So this can be abbreviated as the electron configuration of neon with 1 additional electron in the 3s orbital. So this makes it a little bit more clear that these elements have something in common. They both have 1 valence electron in addition to a full noble gas configuration. Because of that, these elements, sodium, lithium, and also all the other elements in that alkali metal family, are very reactive and form ions with a +1 charge. So it's kind of like the sodium element has the perfect electron configuration, but 1 extra electron. So like a kid being sent to school, like he's got the perfect outfit, he looks like all the cool kids in school, and then it's chilly, so his mom makes him wear a dorky hat. Once he gets to school, what is he going to do? He's going to shove the hat in his locker, lose the hat, once mom's not looking. So that's what these elements want to do as well. They want to get rid of this electron that's making them uncomfortable, making them not like the cool kids, the noble gas elements that they want to be like. So they form +1 ions. When they form a +1 ion, or when sodium forms a +1 ion, it has 10 electrons. And when it does that, now it looks just like neon. Now its outermost shell is the 2nd shell, which has 8 electrons in it, and it looks just like neon, and that's what it wants to look like. Oxygen has 8 electrons, so its outermost shell is level 2. And there are 6 valence electrons in that. Oxygen is in the second period, so we have to go up to the first period and all the way to the right to find helium if we want to write the abbreviated electron configuration for oxygen. Oxygen is like helium with its full number 1 shell, and then it has 2 more electrons in the 2s orbital and 4 more in the 2p orbital. So oxygen has 6 valence electrons. It really wants to have 8 like the rest of the noble gases. So to get those 8, it usually forms a -2 ion, which gives it 10 electrons. Now it has 8 electrons in its outermost shell, and it looks exactly like neon, or like the sodium ion here. Okay, sulfur has 16 electrons. Its outermost level is level 3, and it has 6 valence electrons. It is in the same family with oxygen, so it has that similarity there, that family resemblance. So for sulfur, it's in the third period, so you have to go up to the second period and find neon. This is the electron configuration of neon, those first 10 electrons. So it is just like neon, except then it has 6 more electrons in the 3s2 and the 3p4. So when you write it this abbreviated way, you can definitely see the family resemblance with oxygen. Bromine has 35 electrons. So here is how these 35 electrons are filling up. The outermost shell is the level 4, so it has 7 valence electrons. If we go up a level and all the way to the right, we see that this part over here is the same electron configuration as argon, those first 18 electrons there. And after argon, it has these 17 more electrons in it. It's actually only 1 electron away from being like krypton and having a full set of 8 valence electrons. And so bromine tends to form a -1 ion. This doesn't look very good. It's supposed to be a bromide ion, which has 36 electrons. So that last electron fills the 4p orbital. Now it has 8 valence electrons in that outermost 4th level. And if you compare, you can see that the electron configuration looks just like krypton now. So that is why bromine likes to form a -1 ion. And oxygen likes to form -2, and all these other ions that we've already learned about. So the formation of ions in these main group elements is fairly straightforward because the outermost shell is what's being worked on, either the s orbitals if you're in the alkali metals or the alkali earth metals, or the p orbitals if you're in the other main group elements. But the transition metals are working on their d orbitals, and their ions are a little bit trickier to form. So let's take a look at those. So remember, when you ionize a transition metal, they're going to lose their outermost s electrons first. Even though the last electrons you're listing are the d orbital electrons, the ones that they lose when they ionize are the s electrons. So they're not the last ones in line. That's what makes it a little tricky here. Let's show what we mean by writing the electron configuration of the element before we try to write the electron configuration of the ion. So that's probably what you should do for transition metals. Alright, so here are the transition metals we're going to look at. I added an extra one, nickel, over here, just to try to illustrate a little bit better what I'm talking about. So let's start with zinc. It has 30 electrons. So these 30 electrons go into the orbitals in order. So we finished with the third period, and then we're starting on the fourth period. The third period noble gas is argon. So zinc looks just like argon, except then it has 4s2 and 3d10 after that. When it ionizes, it loses 2 electrons, and it's going to lose them from the outermost shell, which is the 4th level. So it's going to lose these 4s electrons before it touches any of the electrons in the 3rd level. So the 2 electrons that it has lost are the 4s electrons, making it look like argon with 3d10. So I wrote the nickel up here to contrast this. If you just counted the electrons, lost those 2 electrons first, and said, oh, I'm just going to write the electron configuration for something that has 28 electrons, you would end up with something a little bit different. So when you get to the end for the 3D, you would only have 8 electrons left. So nickel looks like argon, 2 in the 4s and 8 in the 3D orbital. So even though nickel and zinc ion both have 28 electrons, their electron configurations look a little bit different. You don't lose the last 2 from the d orbital, making it look like nickel. You lose this 4s. You lose these 4s electrons, making it look a little bit different from what nickel looks like. So just be careful when you draw the electron configurations of transition metal ions like that. Let's just try one more example before we finish this section. With 26 electrons, iron. So once we get to 4s2, those 2 bring it up to 20. It has 6 left to go into the 3d orbital. All right, to make an iron 3 ion with 23 electrons, we have to lose 3 electrons. We're going to lose these outermost 4s electrons first, those 2, and then we're going to pick on the 3d, which is the next in line. So we have iron looking like argon with 5 additional electrons all being in the 3d orbital. So just be extra careful when you form these ions of the transition metals. Make sure you lose the outermost s electrons first before you start digging into those d electrons.